Hi, my name is Ngao and today I will be presenting my research on how cryptographic algorithm performance for securing the messaging system. So when we use apps like WhatsApp, Messenger, or Signal, Facebook, whatever, we're expecting that our message to be private and secure. But have you ever wondered what happened behind the scene? These apps use complex mathematical algorithms to protect our data. The choice of which algorithm to use involving important trade-off between security, speed, and compatibility. So my research here will investigate this trade-off through empirical testing. So the core problem here is securing messaging app need to protect three main things. First is messaging privacy through encryption, message integrity through hashing, and user identity through digital signature. But different algorithms perform very differently in the real world condition. So that is why some work better on new phone, some work better on old phone. So some are fast but lack of advanced feature, right? So my goal here was to measure these differences systematically. So let's start right here. I can see I have selected 6 industry standard algorithm, SHA-259, 1256, and Black2B for hashing, AES-256, GCM, and ChaCha20 for encryption, and RSA-2048 and ADD-25519 for digital signature. I test each algorithm across 4 message sizes, from 1 KB text message to 1 MB photo attachment, to see that each test run will run 30 times to ensure statistical accuracy. We were using the high precision timing to measure performance. So you see, I input all the library here. I define my datasets, creating dataset over here, and I define the time function, define this is accuracy and the time for computational. So let's come to the hashing. So with the hashing algorithm, which verifies the data integrity. So here I'm testing the SHA-256, which is the Black2B. So I will run this one. So as you can see, benchmark will be different across the trial time, but I will use the first time that I get. This on the screen, the graph I the first made. So as you can see, the SHA-256 process this 1 KB message in about 0.003 millisecond, while Black2B is take 0.005 millisecond. Now look at these complete result across all message size. We see a clear pattern that SHA-256 is consistently 2.8 times faster. It's achieving 1.54 gigabyte per second compared to Black's 2B with the 548 megabyte per second. So this performance advantage comes from the hardware acceleration, which is modern processor have a special instruction, special algorithm that optimize the SHA-256 calculation. So let's come to the encryption algorithm. So I test the AES-256 GCM against the ChaCha20 Poly 1305. Both algorithms provide authenticate encryption, meaning they both encrypt the message and verify its integrity. The AES-256 GCM processing 1 MB message in 0.95 millisecond, while the ChaCha20 takes 1.35 millisecond, is a 42% performance difference. However, this advantage depends entirely on the hardware support. AES acceleration is common in modern device, like right now, like what I'm using, but absent in the older one. So they explaining why secure the messaging protocol supports both algorithms. They optimize for performance where possible while maintaining the broad compatibility. Here is the digital signature. This is the most dramatic difference appear in the digital signature algorithm. So I see a signature, yeah, okay. So which authenticate the user and enable the key exchange. So what should happen when I generate the cryptographic key? The RSA key generation take about 45 milliseconds, while ADD-25519 complete in under half a millisecond. So the comprehensive results show that ADD-255 is 93 times faster a key generation and 4.4 times faster a signature operation. This performance difference had profound implication. The faster key generation enables frequent key rotation, which is the foundation of forward secrecy, a critical security property that protects the past message even if current key are compromised. So this empirical result revealed 3 security insights. First is that hardware acceleration create performance tiers that influence the real-world algorithm adoption. Algorithm with the hardware support dominate on the compatible devices. So secondly is that modern elliptic curve cryptography, like at 25519, is enable security properties that were previously impractical due to performance constraint. And lastly is that cryptographic agility, which is supporting multiple algorithms. This is essential for cross-platform security. No single algorithm performs optimal across all devices, so technically there's no size fit all. So in conclusion, the research demonstrates that the cryptographic algorithm selection involve complex trade-off between mathematical security, performance characteristic, and development constraints. The benchmark invalidated why modern secure message protocol have adopted and for the specific algorithm combination we see today. So as we transition toward to the post-quantum cryptography, this performance-aware that evaluation methodology will become increasingly important. So all the code, data, and analysis will be available on my GitHub repository for verification and further research. So thank you for your attention.